In this continuation of the branch prediction lecture, we're going to look at the feedback from the prediction into the branch predictor and then the recovery in the case of a misprediction. So first, let's look at the feedback of the bimodal predictor, the predictor that we saw earlier on. This is the simple predictor that uses a few bits from the program counter to index a single PhD table. And the PhD table contains the 2-bit saturating counters for each one of the branch to where the branch is mapped in the PhD table. So the feedback consists in updating that 2-bit counter. For example, if I need to make a transition of state, say, let's say from weak not taken to strong not taken, or in any direction in that finite state machine. One of the questions is, when do you do this update? We will consider three choices. One is to do the update at the fetch stage. At the fetch stage, I only know the prediction, assuming that I was able to compute the prediction in one cycle. I will know the prediction, and that's the only information that I have to update the predictor. At the execution stage, I know the outcome of the branch. I know whether this branch will be taken or not. However, we need to consider that this branch may be executing in the speculative path of another branch. So I do not know whether this branch actually should be executing. And if I update the predictor with the result of this branch, I may be updating the predictor based on a branch that should never have been executed. And the third option is to do the update at the commit stage. At the commit stage, I know that this branch is committing, so I know that this branch has to be executed. And and of course, I know the outcome already because I have known the outcome since the time of the execution stage. So let's consider these three choices. What happens if I do my update at the fetch stage? If I do the update at the fetch stage, I will only be reinforcing the prediction in the bimodal predictor, and I do not know whether my prediction was correct or not. If I do my feedback at the execution stage, then other predictions of the same branch may have already been done. So the same branch may have been fetched again, and I may be doing prediction of this branch with an old state of the predictor, because there is, in this figure, the execution stage is just 2 cycles down from the fetch stage, but in a real machine, there are many cycles in between the fetch stage and the execution stage. And in an out of order machine, as I said before, the branch may be in a speculative path, and those branches will also be contributing to the update of the predictor. If I do at the commit stage, well, I am even much farther down in the execution time than when I did in the execution stage. Therefore, I can have even more branches that have been predicted based on the old state before I managed to update the predictor. So there is one minor typo in the textbook that I want to draw your attention to so that you're not confused when reviewing this, is that on page 137, where they printed prediction, they should have printed update. So let's talk about the feedback in the bimodal predictor. What is the performance implication of doing the update of the bimodal predictor, either in the execution stage or in the commit stage? And studies have revealed that for the bimodal predictor, where you do the update of the prediction makes very little difference in performance. For the bimodal, updating is usually done in the commit stage, because then you avoid polluting the branch predictor with the outcome of a branch that are only being executed speculatively that will never gonna commit. The next question that we need to address is whether my predictor should be local or global. So let's look at that picture so that it's easy for us to understand the difference. So let's say that I have many different branches that are executed in this program, and I'm predicting this branch that I have highlighted in yellow here. So if I'm using a local predictor, I am only looking at the history of the branch that is being predicted. The outcome of the branch that happened before this branch in the execution path have no influence on the prediction. That's why I call it a local predictor, because I only basing the prediction in the local history. Now, if I look at the outcome of a number of the previous branch that got executed before this branch, then I'm doing a global branch prediction. In a global predictor, I use the history of other branches that have preceded this branch in the execution path of the branch being predicted. So what's the motivation for a global prediction? Let's take an example of a very simple code that comes from an actual spec program benchmark. And in this code, I have a test that says whether A is equal to, that's my branch one. And then if A is equal to, I'm gonna make equal 0. And then I ask whether B is equal to. If B is equal to, I also make B equal 0. And now I ask if A is different than B. That's my third branch, B3. And then I have some statements that come after that. The point here is that if the branch B1 and the branch B2 are both taken, then I know that the value of A and B will be both zeros at the branch 3, and therefore I know for sure the branch 3, B3 is not taken. So there is a correlation between the outcome of the branch B1 and B2 and the outcome of branch B3. So for capturing correlations like this, we're going to look at a correlator predictor. What is a correlator predictor? It uses a PHT in the same way as the bimodal predictor with two case saturating counters. But when I'm indexing this PHT, instead of using a few bits from the program counter that identifies a single branch, what I'm using now is a bit vector that's formed by the outcome of the branch that have been executed before this branch. So that set of k bits there are the outcome of the k most recent branch that got executed when this branch is about to execute. So how do I maintain that global history? Is just a shift register. Whenever I learn the outcome of a new branch, I shift this outcome to in the rightmost bit of that register, and I lose the leftmost bit. So it's a rotating history or a shifting register. This way, when the history that leads to a branch change, I'm going to be selecting a different counter for the prediction, and therefore I'm able to capture these correlations. So this is called my history register. So I insert 1 to the right when a branch is taken and 0 when a branch is not taken. And the shifted out bits are lost because that's history that I'm no longer paying attention to. So this is a two-level predictor because I use the history in the first level and I use the saturating counter in the second level. So when I have an issue when I do the update in the correlator predictor. What happens is that I'm going to update the PHT in a non-speculative way at the commit stage. So what is the problem that would have with the commit stage non-speculative update of the global register? Let's take a look at what happens here. This is the same example that we saw before where we have branches B1, B2, and B3. And let's say that the prediction of B1 happens at time t, prediction of B2 at time t plus 1, B3 at time t plus 2, and the commit of B1 is at time t plus 5. So if I am updating the global register only at the time of the commit of B1, what will going to happen is that the branch B1 and B2, the history of branch B1 and B2 is not included in the prediction of the branch B3. And as we established, what we are trying to capture is the correlation between branch B1 and B2 with branch B3. So if I cannot see what happens in the most recent execution of B1 and B2 when I predicting B3, I have lost that correlation that I was seeking when making this design. So we're going to have to fix that. How can we fix that? So what I have is that, for example, I can have mispredictions, I can have cache miss that will affect the commit time of earlier branch. So if in a more complex code, for example, if the value being tested by B1 and B2 comes from a load instruction and I have a miss in that those load instructions, the delay to committing B1 will be even longer, and are going to have even more branch that will be predicted without knowing the outcome of B1. So we need to fix that. So the effect of this, as I said, is that consecutive predictions of a branch may be using different ancestors of the branch, even if the path leading to that branch is the same, and that's because I have these delays in the commit of the branch. So the solution that we're going to have to this problem is that we're going to update the global register speculatively when the prediction is made. So whenever we make a prediction, we're going to push that prediction into the register, and we're going to use that prediction as our history. So now we have a new problem that we have to solve. We're going to need a repair mechanism because I am injecting bits into the history, and these bits may be wrong because the branch that I'm executing right now may be speculative. So if I have a misprediction, I need to go back and restore the value of the global register that I had when I made that misprediction. So how do I solve that problem? I'm going to have to create a repair mechanism for this correlator predictor. So what I'm going to do at the decode stage, I'm going to create a FIFO queue of histories. And I will checkpoint the current global history into this queue. So whenever I'm making a new prediction, I'll make a copy of the current values in the global register and push that copy into this queue. At the commit stage, age will be the head of the queue, and the corresponding checkpoint for the global history register is this head of the queue. So if I have a correct prediction, then I can simply discard this head of the queue because I don't need it. I made the correct prediction. There is no correction that's needed. If I have an incorrect prediction, then I can shift the branch outcome into age and make it the new global register. So that's how I'm going to be restoring is by popping that value from this stack from this queue where I'm storing it. So let's see. So another observation is that this prediction is also called the global predictor because I have one global register and I have one PhD table. So both decisions are based in a global structure that is used for all branches. So let's go back to the idea of the global register checkpointing and see how we implemented this. So I have, when I'm doing the prediction, I have a current value for the global register. That's the history that I'm considering. In this example, I'm considering the outcome of the last 5 branches. And the outcome of the last 5 branches will index into a given position in my PhD. And that prediction is what I'm going to use for fetching the next instructions after that branch. What I'm going to do, I'm going to shift the global register. So notice that I have lost the leftmost one here, and I'm left with the last 4 bits of the global register. And then the next thing that I'll do, I will take the predicted branch result. Let's say that it's a 1, and or the value that I made the prediction for. So let's say that I predicted that this branch is taken, and I will negate that value, and I'm going to push a 0 into the shift register to put that into the FIFO. The reason that I put in the negation of the prediction is that I only gonna use the value that is in that FIFO if I am wrong. If I am wrong, I need to have the complement of the value of the prediction. And so therefore, by storing the complement in the least significant bit of the global register, I'm going to have the correct history when I need to restore. So I'll push this value now into this FIFO of all the global registers. And when it comes to the time of using this value, so if I find out that this predictor made the wrong prediction, the value will be at the right position in the FIFO to be popped to restore the global history at that point. So there are some issues with the correlator predictor. So if I have a small PHT, the performance of the predictor is worse than if I use a local predictor such as the bimodal predictor. Also, the correlator predictor does not use the location of the branch in the program for the prediction. And so I can have some aliases with the correlator prediction with branches that are in different places in the program, but they happen to have the same history leading to them. So I can introduce too much aliasing when I using the correlator predictor. The solution for this aliasing problem is to reintroduce the program counter when indexing the PHT. So this leads to a new predictor. This is my G-share predictor. What I do in the G-share predictor, I get the K bits from the PC like I had with the bimodal predictor. And then I take the global history and I hash those 2 bit vectors to create a new value. That's the value that I'm going to use to access the PHT. In hardware, for this kind of application, the preferred hashing function is an XOR. I simply do an XOR between the K bits of the PC and the K bits of the global register. So what's the accuracy in the use of the G-share? So when measured with spec floating point 95, it gave an almost perfect prediction and about 83% accuracy for the spec int 95. For some programs such as Go, the accuracy will drop to 65%. What we have today in current processors are much more advanced predictors, and we're going to study the Tage predictor later, that are much more advanced than the G-share predictor, for example. But the G-share predictor was implemented in the AMD K5, in the Sun UltraSpark, and the IBM Power 4. So several real processors that have existed in the past have used this predictor. So back to our example, remember our double nested loop that we saw in the first part of this lecture, and we are interested in predicting the branch at the end of that inner loop. So if I assume that n is equal 4, so it means that that inner loop is iterating 4 times. So if I have this 4 iterations, what's going to happen is that the bimodal predictor will mispredict 1 out of 5 times, because remember, it will going to do the correct prediction, and then you're going to miss 1 of them. The global predictor will mispredict between 0 and 5 times, depending on other branches that are in the loop. And but if I look at this branch has a fixed pattern. It has 4 taken, 1 not taken. That's the pattern of this branch. It executes 4 iterations of the inner loop, and then it does not take the branch to fall to the next loop. So the question is, how could I learn this pattern? And I could remember the history of individual branches when trying to learn this pattern. So we need predictors that are more attuned to the locality of the individual branches. And again, I said that in future lectures, we're going to see much more advanced predictors, such as the TH predictor, that do exactly that. They look at much longer histories and try to learn the individual history of specific branches. So we have studied so far two global predictors. The bimodal predictor that we studied earlier is a global predictor because you have a global hash function and a global set of counters that you select. There is only one set of counters. And the G-share predictor is also a global predictor. So there is a single global way to do the index, and there is a single global predictor. Now, a global set predictor is one where I still have a single way to do the addressing, but now I have multiple, I have a set of PHT instead of a global PHT. So in the first level, I have a global shift register for the correlations. So I selecting a position in the PHT based on my history, my global history. And then I select one of many PhDs based on bits of my program counter. So I have the set of multiple PhDs, and that is to prevent aliasing. And so this is the global set predictor. It is expensive in terms of storage because you have to have more PhDs, and it must use a few PhDs to be viable. Although you're going to see that in the TH predictor, we may have many tables that we use in current state-of-the-art predictors. Another type of predictor is the set global predictor. So in the set global predictor, what is going to happen is that I'm going to have many histories. So in this case, I take some bits of the PC, and those bits of the PC are used to select a history vector that I'm going to use to access the PhD. This the state-of-the-art TAGE predictor has resemblance of that because it does maintain different lengths of history when it's trying to do the prediction. Again, we're going to see more details of that later. So here I have a set of branch history registers that will be selected from using some bits hashed from the PC. And then I have a single global PHT. So that's why this is called the set global predictor. So I use the history that I selected to select a specific enter of the PhD. Now I can have a set predictor. So a set predictor does both things. It uses some bits of the PC to select one of the branch history registers to select which one of the counters in a given PHT will access, and use other bits of the PC to select one of many PhDs. So I have a set of branch history registers and I have a set of PhDs. So this bits will select the history, and this bits will select which is the PhD that I'm going to use. And I will select, of course, use the selector history to find the PhD entry that I'm interested in. So this is what I had for the second part of this lecture on branch predictions.